A checkout page looks like one app, until one API pod dies and orders stop moving. On a single server, recovery is manual. Restart the process, clone capacity, and hope someone notices the failure fast. Kubernetes changes that job. You declare the target, and the platform keeps reconciling the running system toward it. Start with the cluster. It is the shared operating space made from nodes. The nodes provide CPU, memory, and networking capacity, and Kubernetes decides where each workload can run. The front-end container does not run directly as an isolated idea. Kubernetes wraps one or more containers in a pod. For most application services, you can think, one running copy of the app means one pod. A deployment says how many copies should exist. If ShopWave needs 3 orders, API pods, the deployment owns that target and keeps creating or replacing pods until the target is true again. Pods are replaceable, so other parts of the app should not depend on pod IPs. A service gives the orders API a stable internal name and routes traffic to healthy matching pods. For external users, traffic usually enters through an ingress or load balancer. That edge rule sends browser requests to the front-end service, which then talks to the internal API service. Configuration should not be buried inside the container image. Config maps and secrets let the same application image receive environment-specific settings and sensitive values at runtime. Now follow one checkout. The user hits the site, the request crosses the edge, the front-end pod serves the page, and the front-end calls the order's API through its service. The API then talks to data systems. PostgreSQL stores the order, Redis supports fast state, and the application code reaches those dependencies through stable names rather than fragile machine addresses. If one API pod fails, the service stops sending traffic to that unhealthy copy, and the deployment creates a replacement. The incident is still real, but the platform narrows the blast radius. Scaling in Kubernetes usually starts by increasing replicas. Instead of one order's API process, taking every request, several pod copies share the load behind the same service. Readiness and liveness probes matter because they turn health into routing decisions. A pod should not receive customer traffic until it is ready, and a stuck pod should be restarted instead of silently staying broken. Autoscaling can add pods when load rises, but it does not remove every bottleneck. If the database, queue, or external dependency is the limit, more pods can amplify the pressure instead of fixing it. A production cluster also needs boundaries. Namespaces separate teams or environments, and RBAC controls who can read, change, or deploy resources inside those boundaries. You still need evidence. Logs explain what the app said, metrics show resource and request behavior, traces connect slow paths, and events show what Kubernetes changed underneath. Delivery becomes safer when changes move through reviewed manifests. A git commit updates the declared state, the pipeline applies it, and the rollout makes the change visible and reversible. The business value is not that Kubernetes sounds modern. The value is repeatable operations, safer releases, faster recovery, clearer ownership, and a platform that can absorb normal change without a fire drill every time. But Kubernetes will not fix a poorly designed application, a dangerous database migration, missing tests, or unclear ownership. It gives teams better control loops. It does not replace engineering judgment. The professional mental model is simple. Define desired state, route traffic through stable contracts, observe the system, and design for recovery. If you can explain those 4 pieces for one real application, Kubernetes stops being abstract.